Hello and welcome. My name is Nordling and I'm an assistant professor in automatic control at the Department of Mechanical Engineering at the National Shenggong University in Taiwan. I'm also the general chair of this workshop. Behind me, I have the God of Doors, a piece of art created by Lai Jiahong in 1995. These gods, they guard the campus against evil spirits and welcome good spirits. Now it's my pleasure to introduce our honorary chair, Chair Professor Wu, that will welcome us.
It is a pleasure to welcome all of you on behalf of the National Shenggong University in Taiwan. I'm proud that our team, the NCKU Parkinson's disease quantifiers, are one of the finalists in the OpenCV.AI competition. They are also arranging this workshop. Now let us all learn computer vision and AI using the OAK-D camera together.
I'm happy to tell you that we now have over 800 registered participants for this workshop series. You are welcome to subscribe to our YouTube and Twitch channels. And if you wish to be notified every time we post a video, then you can also press the alarm bell button. It's my great honor to present Anna Petrovicheva, CTO of OpenCV.AI, the commercial branch of the OpenCV Foundation, where she is also a member of the board. Anna has been working in the industry for 11 years on almost every possible application of computer vision. And today she will be speaking about vision on edge devices. Welcome and enjoy this fascinating talk.
Hi, my name is Anna Petrovicheva, and I'm going to talk today about the vision on the edge devices. So let me first quickly introduce myself. I'm a part of OpenCV Foundation, and I'm also the CTO of its for-profit arm, which is called OpenCV.AI. In general, my career was tightly connected to OpenCV for the last 11 years, so I've been into computer vision industry and field for 11 years now. I started first as a software engineer and developed something for OpenCV and on top of OpenCV, then switching into deep learning starting in 2014. And up until now, I'm doing computer vision deep learning based algorithms for many different industries with companies from all around the world. So today I'm going to talk about vision on the edge devices, also because my career was tightly connected to the edge devices. The whole presentation today will be split into several sections. First, I will talk about the what, then about the why. I'll briefly cover the history of edge devices in computer vision in the last decade. Then I'll talk about the how, and quickly talk about what I think will be the next big thing for the edge devices in computer vision. Now, as you probably know, OpenCV is the biggest computer vision library in the world, with somewhere between 1 and 2 million downloads in Python PyPy package manager per week. So OpenCV is used in almost every smartphone in the world. It also is in space and underwater, so pretty much everywhere. OpenCV is very tightly connected with the edge devices now, because most of its algorithms and data structures are optimized for edge devices too. Now first, let me talk about what are the edge devices. Edge devices is something that is close to the customer, close to the consumer, or close to the place where the data was captured. It can be something like a mobile phone, a wearable device like smart wristwatch. It can be a stationary camera with some AI capabilities, for example. These devices can be battery powered, like smartphones, or connected to some power outlet. For some battery-powered devices, recently, for example, we were able to create a neural network that works on the same battery power for 4 years. So battery-powered devices are becoming more and more common and widely used. A very important reason for that is that they are way faster and easier to install. You don't need to put the power outlet to the camera that you are installing. So battery-powered devices are also something big and important in the edge devices industry. So why do people run the computations on the edge devices and not servers? So servers are something big that can be either in the data center or in the server room in some corporation or office. So they are definitely capable of all the computations that we would want to run on them, but they do have several downsides. The first is the cost. For example, AWS is awesome. It's probably one of the biggest, most important things that happened to the software industry and hardware industry in the latest decade. But it is also pretty costly. So there are significant server costs that one will need to bear when running the computations there. But it's probably not the biggest downside to the servers. There is when you do the computation in the server, you will need to send the data that was captured somewhere else to the server, which means that you are suddenly dependent on the internet connectivity, which is not awesome everywhere. For example, if we are working with some distant facility or some very sensitive information, it would be very hard to send it through the internet. Specifically, privacy is a big concern here, because it's definitely better if some types of data never leave the device where they were captured, right? So this is sometimes a nice to have clause to only have this data stored in this device and not somewhere else. And sometimes it is a must-have. For example, if we are working with some sensitive data, for example, we are installing cameras in some corporate office, we would be able to see not only the faces of the employees, but also some sensitive documents there. And these data can never leave the devices, can never be sent anywhere. In most cases, the devices that do these computations, they don't even have the capability to send this data to be 100% sure that it's not possible to send this data, even if the devices were hacked. So there are some severe regulations about the privacy, for example, GDPR, that also would favor a lot computations on the edge devices versus computations on the server. And that is why recently, for the last 5 years, there's been a very big and important trend in computer vision about switching from server computations to mobile and edge devices computations. Now let me briefly talk about the history of how edge devices were important or not important in computer vision for the last decade. So when I started being a part of computer vision, it was 2010, 2011. We mostly worked with 100% worked with classic computer vision, and it was very much optimized for the edge devices. So we had them working, we had the algorithms working in real time or somewhere close to real time. You know, in many papers, there is a notion of kind of scientific real time, which means that it is not real time, but it's close, close enough to kind of name the paper real time something, when in fact it is not. So in many cases, we had scientific real time or we had real time. One of the devices that I worked most with at that time was NVIDIA Tegra and Qualcomm Snapdragon-based processors. They already had some specific optimizations for procedures that were close to what we did in computer vision. At that time, the algorithms were mostly built, that I worked with at least, were mostly built on classic descriptors like orb, sift, serve. histograms of gradients and algorithms like that, and heavy equations that were solved with multiple different mathematics methods like SVT algorithm. Chips were definitely getting faster, and algorithms were getting more complex, but the algorithms of the classic computer vision were pretty lightweight, so it was a kind of a standard to have them running in real time. And everything changed when there was a deep learning boom. Deep learning algorithms, as we know, are many orders of magnitude heavier. But when this boom happened, when computer vision switched to using deep learning everywhere, computer vision started working. It was kind of a wide notion of, as if it didn't work before, and suddenly it started really working now and fulfilling the expectations that we had for computer vision. One of the big things was one kind of the big important tasks of computer vision always was pedestrian detection, and the quality that deep learning was providing for this specific task, for example, was kind of showing that this is a really big and important milestone where we will now really be able to use computer vision in some production scenarios, not only algorithmic scientific things. But yeah, it was super heavy, and it is super heavy. It is much more heavier than classical computer vision procedures. And because of that, in the first several years after the deep learning boom, these algorithms were only used on servers. So when they went into production in kind of 2014 to 2015 started, they were only ran on servers because of how heavy they were. Somewhere around 2016 and up until now, the trend changed, and there started a trend and significant kind of movement to go into edge devices. And there were two things again that helped to do that. First was that the algorithms were getting more and more optimal. They were not as redundant as before. Still very redundant, but already kind of suitable for the mobile applications. And second, mobile devices and mobile chips started to support specific acceleration for computer vision and deep learning. This meant that basically there was some specific hardware on the system on a chip that would make these devices work with the neural networks way faster than before. To kind of illustrate that the chip progress is going very fast now, so in 2017 I compared an iPad 2019 versus a MacBook Pro 2017, and it was faster in terms of computer vision, in terms of deep learning. So the progress there in terms of the acceleration and the hardware architecture was going very fast. In terms of optimized algorithms, many research groups and many companies started working with with the focus not only on the accuracy of the algorithms, but also on the speed. Probably the most prominent example here is Google. They created MobileNet architecture that is super widely used, specifically to work on mobile phones in real time. There are other architectures like that that also employ this notion of performance in its name even. For example, there is a family of architectures called EfficientNet. Again, they are more about the performance than about reaching the state-of-the-art accuracy. So what we have right now is that a lot of neural networks, a lot of computer vision pipelines are being moved into edge computations. And I think that this trend will be continued in the future. Two big things that make me think so are artificial reality industry and robotics industry. So I'm thinking that in the next 10 years, at least I'm really much hoping for that, that then in the next 10 years, these two things will really kick off. We will have more robots working in our everyday lives or in manufacturing pipelines. and we will start having a very nice artificial reality applications. Both these things rely heavily on having a nice computer vision engines. And because of that, I think that we will see a lot of movement to the edge devices again. What's important in both these cases, in artificial reality and in robotics, it's not possible to send the data back and forth from and to the device, because we need to have a very fast feedback. For example, in artificial reality, when we move in the room, we want the obstacles to be detected instantly, not after the data was sent to the server and got back to us. Same goes for robotics. And because of that, I think that this trend will only get stronger, and more computer vision algorithms will continue to go to the edge devices, meaning that there will be an advances both in the algorithmic side and in the hardware side. Now let me talk about the how. How are computer vision algorithms even getting on the edge devices? Now there are three components to that. Hardware, software, that splits into two kind of parts: software as the tools, and software as algorithms. Let me first speak about the hardware. Now, I'm not a hardware specialist. I only work with hardware as kind of the software developer that needs to understand the kind of how hardware works in order to make deep learning and computer vision algorithms that we develop run faster on this type of hardware. But yeah, I do know something about this hardware, about how the hardware is built. And there are several, I would say two important things that happened in order to make deep learning faster on the hardware, on the edge hardware, importantly. Now, first, it's rather common right now to have a specific computation unit on a system on a chip that would be responsible for the computations related to deep learning and artificial intelligence. In essence, it's typically a very fast matrix multiplication unit, because most of the computations that are done inside a neural network are essentially matrix multiplications that are done to compute the result of each convolution. Now, in marketing materials, these models are typically called something like artificial intelligence models or accelerators, but again, typically this is a matrix multiplication hardware. The devices can actually be pretty different in their form factor, and kind of function. This can be a separate accelerator. These operations can be implemented on GPU or NPU, like neural processing unit, in the system on a chip. Sometimes these computations also employ the use of DSPs. And the second important thing that happened to the hardware is that the data transfer between different units on the hardware this transfer was significantly optimized using two things: bigger memory, bigger caches, which means that more data can fit into the cache, and we don't need to copy data many different times. And second is faster data transfer. And a good example here would be the OpenCV.AI kit that made the story behind that. There is an Intel neural compute stick that has MyVideos on board, MyVideos Mirrored X on board, and there is Oak that basically uses the same processor. Even though these processors are the same, these two devices provide dramatically different speed of the processing, because in neural compute stick it has a USB interface, which means that the data from the camera is being transferred through USB, which is not the fastest way to transfer the data. Now, the team at OpenCV.AI kit in Luxanas, they were able to remove the USB from the scheme, transferring the data directly to the MyVideos chip, basically optimizing this whole processing time orders of magnitude just because of the data transfer. Okay, so this is about hardware. Just again, to repeat myself, matrix multiplication units, different names, but more or less the same kind of goal, and optimizing the data transfer does it. Now let me speak a bit about the tools But before I'm speaking about the tools, let me just, briefly describe how does it happen? How does a computer vision, like deep learning algorithm, how it is moved into the target device? For example, let's speak about mobile phones, just to be clear. But the process is pretty much the same for other small edge devices that I was mentioning before. Now, typically, the process is the following. The neural network is being trained in some framework. There are two big frameworks that are rivaling in this space right now, Pytorch and Tensorflow. I will just say that Pytorch is my favorite way to train neural networks, and I typically use that, as well as my team. So the neural network is being trained in Pytorch, then it is being converted to Oneness, or different or similar intermediate format. And then, as a third step, it's being converted into the edge framework. Edge frameworks are something that is specifically optimized for target edge device inference. So several examples here are TF-Lite, OpenVINO, TF-Lite from Google, OpenVINO from Intel, TensorRT from NVIDIA, and CoreML from Apple. Typically, the training process with Pytorch, it happens in Python, and the inference process with TF-Lite, Oneness, and TF-Lite, OpenVINO, and other networks, other frameworks, happens in C++. So this process is converting the model and converting to another language, converting the pipeline to another language. Now, why do we actually need to do that? The answer is the following. Some frameworks are good for training, and some are good for inference. Now, there are definitely a lot of efforts to fight that. For example, there is a Pytorch mobile that promises a very fast inference speed on mobile devices, but just because how this industry is built, the situation right now is that the frameworks that are produced by the hardware producers, hardware providers, are typically faster than that, for many reasons. For example, let's take OpenVINO, because I personally know a lot of people behind OpenVINO. So in OpenVINO, once a new generation of the processors reaches the market, there are already some specific optimizations for these processors. Now, OpenVINO team may want to contribute these optimizations into other toolkits, but this may be happening in several months, right? It doesn't happen immediately. Also, the optimizations in OpenVINO is built specifically to work fast on Intel devices, which is not necessarily true for other frameworks. So typically, at least now, the frameworks that are created by the hardware provider are just faster than other frameworks. Again, there are exceptions in this case. Let me speak about the second step in this scheme. So once again, we train a network in Python with Pytorch, then we convert it to Oneness, and then after that we convert it into the edge inference framework that we already discussed. So Oneness is actually a very big deal. Before that, there was actually a need to convert every different training framework result into every possible inference framework result, inference framework model. For example, if you trained a model in, well, at that time that it was Kathy, you would want to convert to some weird inference engine there. You would need to implement a direct conversion from Kathy to this inference engine. Oneness solves the problem by reducing the need to have this square complexity of converting every framework to every framework. It means that you can convert all the frameworks into one Oneness and convert the Oneness result into every inference framework, which is linear complexity in terms of the number of the frameworks versus square complexity that was before. Oneness is a standard that describes how the neural networks are stored. So it is a format that everybody more or less agrees upon, right? That it's kind of something that works, something that describes how the models are stored, and can be used just as an intermediate format to convert from A to B. Now, Oneness is not perfect. It is limited because it's a standard, right? It cannot support every new cutting-edge layer with complex name, but it works, and it is accepted by the industry as the best possible way to work with different training and inference frameworks. Now, the process of conversion from training to inference code is almost never straightforward. I probably have never seen it happen in, without any issues. How it happens is the following. So a prerequisite to start this process is having a Pytorch network. I'm talking Pytorch, but you may use any other framework like TensorFlow or maybe something different here. But you need to have your model in this framework that works, that satisfies you by performance and by accuracy. And ideally, you need to have a test for that. Now, I'm a big fan of tests. I think that even though we are data scientists, it's our obligation, our professional obligation to implement good code, and tests are definitely a big part of implementing a good code. Being able to test it and validate it is super important. So ideally, you have your network that you are happy with, and a test that verifies how it works on a specific image or data set, maybe small data set. Now, first you do Pytorch to Oneness conversion. There are libraries, there are specific ways on how to do this, but it's almost never straightforward. If your Pytorch network has some dynamic shapes, for example, it has view and it has some dimensions not fixed there, it will mean that the Oneness conversion will most probably not work. You will need to get rid of almost all of the dynamic operations in Pytorch to be able to convert it to Oneness. Now, when you fixed it, what you do is you test your Oneness model. There is a way to infer the data through the Oneness model, and you need to verify that the results are 100% the same as in Pytorch. By saying 100% the same, I mean that the results are same up to 4th digit after the point. So everything after that may slightly differ because of different, underlying math libraries, and that's fine. But if you have a difference in the 2nd digit after the point, you may have some problem in your network. Now, after that, when you verify that the results are definitely the same, you basically look at the Oneness graph. There are maybe some issues in this graph, or maybe some redundancies in this graph, because of how Oneness represents the data internally. Its representation is different from Pytorch and is different from TensorFlow, and because of that, it may add some redundant operations that will not help you, reach the performance that you want. A good practice to do is actually before conversion to the Oneness to get rid of all the batch norms. There is an algorithm, actually pretty kind of simple mathematic procedure to merge the batch norms into the preceding convolution layer, or the next convolution layer, depends. And it already saves you some time on the computation and in the inference time, and also saves you some memory, which is important. Okay, so you looked at Oneness graph, you maybe found some redundancies, batch norms that you forgot to get rid of and stuff like that. You fixed that, now you're happy with your Oneness graph. Now you basically do the same for the second transition. You take your Oneness and you try to convert it into the target framework, for example, TF-Lite. Now, it's important that the data storage formats in the first and last networks frameworks may be different. For example, in Pytorch and in TensorFlow and TFLite, hence, the data storage formats are different. Pytorch stores channels first, and TensorFlow stores channels last. Which means that in some cases you may find that after you converted your ONNX graph into TensorFlow-like graph, look at two-tone TensorFlow-like graph, you will see a whole lot of operations that basically just transition the data back and forth in the memory. This is not something that you want because it's super inefficient. You need to fix that again. So you will need to do something about your graph, something about your data storage to get rid of these data layout operations that change the the order of the channels back and forth. After you are happy with this graph, again, you will need to test it and verify that the results are the same with ONNX and the results are the same with Pytorch. Now, it's important to retest the results in ONNX because if you find that at the last step the results are different from the first step, you actually don't know what the reason is. Something broke at the time when you converted from Pytorch to ONNX or from ONNX to TensorFlow. So just like, a good policy in every data science work, and here too, is to do one change at a time and verify the results. So one more important thing to do when you're converting your pipeline from training to inference, some optimized inference on the edge device, is to convert it to C++. And when you're doing it, you basically need to use a C++ library for your inference framework of choice. And you also need to re-implement pre- and post-processing operations to C++. Now, this typically is not a lot of code. It may be a lot of code, but it's rare. Most probably it's not a lot of code, but it takes some time to implement it. So the last time I did that was 1 year ago, and I spent 8 hours of my time to implement 20 lines of code that would do exactly the same pre- and post-processing steps as in Python. And I know it sounds kind of funny, but it really does take time. Typically, you implement the pre-processing, you start testing it, you compare your Pytorch result, your Python results with your C++ results. They're just different, and then you start, digging why are they different? What is the difference between 6 lines here and 6 lines there? So you basically need to make sure that the results of the pre-processing before they go to the neural network are exactly the same as in Python. Otherwise, things will go badly. Same goes for post-processing. And this is basically it. So this is how the neural networks get from nice, Python trained formed into mobile phones, edge devices, stationary cameras. You converted them into C++, you run them on the device, and then basically you got it. Now, the third part about how to do that is the optimized algorithms that I already mentioned. Now, as I already said, neural networks are super redundant, right? We don't know how much exactly. We can only guess. The reason for that is that there is some underlying theory for neural networks, but it's not extensive enough as of just yet. So we need to kind of guess from our practical considerations and experiments how much redundant is every different neural network. And obviously their redundancy is different because, for example, you may take an object detector that was trained for MS COCO, 80 classes, a lot of big data set, and then you want to use it with a way smaller, kind of less diverse data. For example, you would want to, detect some defect details in the manufacturing process. It's a very, very small kind of diversity of the data that you will get. In this case, if you just take the same network and apply it to different, smaller, kind of easier tasks, the redundancy of the same network will be basically way bigger than it was for MS COCO case. Now, the ways to optimize neural networks they all heavily rely to this notion of neural networks being redundant. And there are three main ways that people use to optimize neural nets. First is quantization. It's not even now kind of a way to optimize neural networks. It is something that you just need to do to work with specific devices. Let me explain. So when you train neural network, it is being trained in 32-bit floating point numbers. When you run the neural network, it may actually be the case when the device doesn't support 32-bit floats. 32-bit floating points is something, something chic to have, something really kind of expensive. And it's not necessarily the case with small battery-operated devices. Many of them, for example, only support 8-bit fixed point computations, not floating points. In many cases, though, for example, smartphones, they do support floating points, but some floating points operations are way more expensive than fixed point operations. And because of that, if you switch into fixed point computations instead of floating point computations, you will again save some time and energy at the inference stage. Now, several options that people use when quantizing neural networks, they go from 32-bit floats into 16-bit floats, which is pretty simple operations to do, into 8-bit fixed point numbers, which is a bit more trickier. And there are some extreme examples when 32-bit floating point networks are being turned into binary or ternary nets. Binary meaning that you only have zeros and ones, and ternary meaning that you also have -1. Now, they are possible. There are some examples, but this is not the mainstream in the industry. So the mainstream is not binary networks. The reason for that is that they are super hard to train, and there is no proof that it is possible to train them for every different task. So it seems that it's possible to train them for classification. It is maybe possible to train them for detection, but it's significantly harder. Now, there are two ways to do the quantization. You can do it while you're training your neural network, or you can do it after you're training your neural network. Obviously, after you trained it, just doing some, operation is easier than doing it when training. Now, the state of the art here was actually advancing pretty fast, and the recent results are that even with post-training quantization, when you already trained the neural network, you take it and you convert it into 8-bit fixed point numbers, the quality drop will only be several percent, like 2 to 3%, which is actually awesome. This was not the case kind of several years ago. So the quantization algorithms are really, really important to make your network work on the edge device. The second way to optimize neural network, again very much relying on the redundancy of neural networks, is called pruning. So it means that when you're training the neural network, you try cutting some layers, not layers, you try cutting some channels inside some layers, convolutional layers, and you just, tune the network without them. So for example, you decide by some heuristic that you want to, you have 32 channels in your layer number 4, and you would want to cut the channel number 5 completely and tune without it. See how it goes. Now, typically there are several kind of different heuristics, simple or complex, on how to choose which channels to cut while training. For example, a pretty good heuristic is just to select the channel with the smallest mean weight for this channel, or with the smallest mean result after this channel, right? So kind of the logic behind that is there are some channels that are very close to zero, they zero out their weights or they zero out their results, and basically they are meaningless. Now let's try to get rid of them and see what happens. There are obviously other ways to, select which channels to cut. You may want to find some linearly dependent channels. There are some, and it's proved that neural networks, they do have some linearly dependent sets of channels, and if you kind of get rid of one of them, theoretically the result will not change. So one of the ways to prune neural networks is to do that. But the most common way to optimize a neural network is just to start with something small, start with a small backbone. Kind of backbones in the industry, they are kind of split into the kind of state-of-the-art accuracy and state-of-the-art speed, right? And you need to start with something efficient in order to be able to fit into some real-time requirements or small edge device. For example, mobile nets from Google, they did a really big thing in the industry. They are very widely used. There were several generations to them because they do work. But you cannot just, take mobile net, put it into your specific case and be happy about that. It's almost never the case. So the process is that you just start with something small, like mobile net, and you iteratively do sets of experiments, changing one thing at a time, doing the following. So you try to cut the mobile net here and there, you run the experiment, see how it goes, see what is the quality drop or maybe even gain, and repeat the same. So try to cut it again here and there and see how it affects the quality. Essentially, you are trying to find the sweet spot between the accuracy and the speed of the network. You want to create something that is pretty fast but also accurate enough for your target case. A good policy here, when you do this kind of iterative process of cutting your basic backbone, is to set the desired metric on the accuracy that you would like to reach, and try to optimize the speed as much as possible without dropping the accuracy below your target threshold. For example, you may say, okay, everything that's above 90% is good for me, and then you kind of work only with the set of the networks that are higher than 90%, that give the results higher than 90% accuracy, and you try to optimize them as much as possible. Once your network drops lower than 90%, for example 87%, you say, okay, this was a bad change. I probably don't need to do that in the future. Okay, let me speak just a bit about what I think will be the next trend for the next 5 years in terms of the edge device and computer vision in general. So probably somewhere from 2018 we are living not in kind of research scenario, but we are living in kind of industrialization scenario, which means that previously we had a lot of different moving parts in terms of how to do neural networks. Nobody kind of had a direct answer to them. Now it seems we have it, and the problem is not in how to do neural networks, but in reliability, in good tools, in testable pipelines and stuff like that. Now, previously, kind of before, when deep learning only kind of appeared on the scene, like after 2012. It was kind of a black magic type of scenario where there was some data scientist doing some black magic, and then kind of it maybe worked. Now it's not this case anymore. It does work in a very specific set of conditions, a set of kind of tasks, and we know this set of tasks. And the question is how to make it work for your specific task. There are kind of ways to estimate whether your task is within the realm of possible. Now, there are two options for the next 5 years that I see. First is that this kind of process of industrialization of deep learning will just continue. And in this case, we will see more and more standard, high quality, high performance solutions that work. The second option is a new algorithm or technology leap here. And maybe transformers kind of signal and candidate for this new technology leap. In this case, we will again fall into the kind of black magic type of scenario of research, not knowing what is the right way, and working with the servers for a couple of years in order to reach the state of the art. After that, in several years, it will all calm down, and we will again start moving some of the algorithms into the edge devices by optimizing the hardware and optimizing the algorithms. Now, this is it for me today. I would be super happy to answer your questions, and thanks for joining.
Hello, everyone. We now move on to the Qra session, and we now have Miss Anna online to answer our question. Do you want to say hi to everyone?
Hi, everyone, and thanks for joining.
Okay, and I will speak the question from YouTube. First question is, what battery power devices was it that you managed to run a neural network on for 4 years that you mentioned in the beginning?
Yeah, it was. Thanks for the question. And it was a battery-powered device operated by a RISC-V architecture-based chip, right? So RISC-V is a new open source architecture that is probably going to be something big and important in several years from now, and is already gaining a lot of traction. One of the good things about that is that you can actually build very low power chips with that architecture that would consume like not a lot of battery power, but still will be able to run neural networks there. Please keep in mind that this is not real-time mode, right? This neural network takes several seconds to infer on this device.
Okay, thank you. And next question is from Akon. She said, thank you so much for the interesting speech. Would you please explain more about the scientific real time? How will the data be collected in the situation if it is not in real time?
Yeah, it's kind of, an internal joke between people who are doing something for production and reading scientific papers, naming something in real time. So in many cases, when some neural network works, for example, 10 frames per second, the paper is already called doing something in real time, when in fact it isn't. So scientific real time is something that is good for, publishing your paper at conference, but at the same time not being real time that can be used in the production.
Okay. Next question is from Winnie. She said, you spoke about how Lucians increase the data transfer speed from the camera orders of magnitude from removing the USB intermediary. How do they transfer the data and how much could it still be made?
Okay, so let me just ask you back. So the question is, how much data transfer can be sped up when we don't use USB data transfer, but rather use something faster, right?
Yes.
Yep. Okay, so a lot, by orders of magnitude, to be more precise, because USB is super slow, and if you want to infer the data in big resolution, especially, it depends on the resolution of the data, but it can be sped up by orders of magnitude compared with USB connection.
Okay. And next question is interesting that you mentioned that one after Oneness conversion must test that it gives the same results up to 4th digit due to change occurring during conversion to the data flow graph. Could you provide an example that can be posted on the washout website?
Okay, so the question is about what is basically the correct kind of precision, how we can compare the results by different, provided by different inference engines, right? So I was mentioning that when you convert to another framework, and you can expect that if you did things correctly, you can gain like almost exactly the same results, except for maybe the digits after the fourth digit after the point, right? So this is basically not from, this is a knowledge that I got not from, deep learning people, but rather from my time that I spent with high computing, high performance computing people, right? In their standards is like, it's the same if the fourth digit after the point is the same. Like the difference starts after this number. So basically, this notion comes from how the floating point arithmetics works on the modern computers.
Okay. And next question is from Rick. I very much enjoy your practical recommendations. Like example, merge batch norms into convolutions. They save memory and computations to remove the operator moving data back and forth in memory. Could you provide an example of how to do these things?
Okay, so how to optimize convolution by not moving the data back and forth in the memory, right?
Yes.
Yeah. Okay, so basically you can do it several ways. I'm thinking, so first is like if you made your convolution kernel small enough, you will most probably fit into the neural compute units, neural processing units, or NPUs of the modern phones, or like ARM chips or something similar. Also, one thing is like basically if you quantized your neural network, then again you will have smaller kind of smaller amount of weights and data to copy to these units, and hence you will basically save time on data transfer. In general, kind of you want to make things smaller to make sure that they fit. It's a general recommendation.
Okay. Our last questions, and because now we run out of time, so maybe we can end up here to end our Q&A sessions. So thank you for joining us for answer the questions. And now we can end here. Thank you.
Thank you so much.
Bye-bye.
Bye.